Now the next thing we want to do is figure out what is Q in. Q in stands for the net amount of charge inside the Gaussian surface that we drew. So that's what we're trying to figure out, is how much charge is inside there. What we know is that the net charge on the whole sphere is Q. So Q in equals net charge inside the Gaussian surface. And our Gaussian surface is a sphere with radius r. So how are we going to figure that out? So here's a redrawing of our picture. There's our Gaussian surface, there's our charges, there's our sphere. If we look at it, right off the bat, we see not all of the charge is inside our Gaussian surface here, okay? Only some of it is. So Q in is going to be a fraction of the net charge. Okay, because some of the charge is outside the Gaussian surface and some is inside. So if we want to figure out what the charge is, let's remember that charge density, so volume charge density rho, is charge divided by volume. Let's use that idea. So if we wanted to know the charge, we would multiply the density by the volume. So the charge inside our Gaussian surface is the charge density rho times the volume of the Gaussian surface. So what are those two guys going to be? So our density is charge over volume. One thing we know about charge is that the net charge Q is applied to the total volume of the sphere. So 4/3 pi times a cubed. So total charge over total volume. So there's our volume charge density. That's a constant value. That doesn't change because it's uniformly distributed. So for rho, we can stick in Q over 4/3 pi a cubed. Volume of our Gaussian surface is a sphere with radius r, so the volume of the Gaussian surface is 4/3 times pi times its radius cubed, r cubed. So let's put all those things together. Q over 4/3 pi a cubed times 4/3 pi r cubed. Our 4/3 cancel, our pi cancels, and we're left with Q times r cubed over a cubed. So there's the net charge inside. Now let's put it together. Gauss's law said that the net electric flux was the integral of E dot dA equals Q in over epsilon naught. Let's write that part down again. Now let's fill in the two things we figured out. The integral of E dot dA works out to be E times 4 pi r squared. Q in is Q times r cubed over a cubed, and that Q in is divided by our constant epsilon naught. Okay, let's simplify things a little bit. We divide both sides by r squared, we're left with an r over here. So E is 1 over 4 pi epsilon naught times Q times r over a cubed. Then if you prefer to write it with Coulomb's constant K, you could say E equals K times Q times r over a cubed. So what this shows us is that inside the sphere, the electric field increases linearly as we go from the center where r equals 0 till we go to the outer surface where r equals a. Right at the surface, we would fill in r equals a and we get kq over a squared. So all this makes sense with what we see here. So here's our electric field inside. Okay, for the next part, we'll find the electric field outside.